Swayam Prabha. Digital India. Educated India.
So one more important topic, please occupy your seats. See, we have seen like how a bio waste can be converted into some useful, particularly the biofuels, okay, that is the one. So another waste what we see in our day-to-day life, every day, everywhere you see that these days, another waste is there, that is plastic. So you need to find a solution for that also, right? So we cannot, last class I told you there is something definition called sustainable society. We should not compromise on our requirements, okay? Instead, make them more sustainable. That should be the case, okay? Just by looking at that plastic is very dangerous, I mean, it's not, we are not able to decompose them, and we don't stop using the plastic. Find a way to decompose, or you find a way to use it for some other purpose. Okay, so a lot of times whenever this plastic question comes, we always get into our mind, why can't the government stop producing the plastic? The first question everybody gets, why governments are not stopping plastic production? Though everybody knows that it is not good, it doesn't decompose. Plastic's lifetime is, I told you, about 400 years. If it on its own, through a natural process, it has to decompose into a small molecules. Okay, it takes about 400 years. Okay, so that we cannot add this one. We cannot wait until that time. Our lifetime is only 70 to 80 years, so we cannot wait that. By the time we will make almost 5-fold, 10-folds of plastic what we are decomposing by a natural process. So which means we need to find out some alternative procedures to decompose. And I told you we cannot stop producing the plastic because it has its own unique advantages, particularly for the some particular materials, some properties, packing. Okay, so you have to have that. Which other, we cannot use always a metal based materials. Okay, so they have some limitations, but plastic has a lot of advantages in terms of properties, so it has to be continued. Only thing you need to find out, how can we actually decompose? Otherwise, you will see the landfills completely by a plastic. Okay, so this is what we are going to learn. There are two ways people we can avoid, decrease the plastic waste. One is called recycling, other one is called upcycling. Okay, I will tell you what is that recycling, what is upcycling. There are slight difference between them. Earlier, we used to learn only the recycling things. That we hear also always. Okay, but now the upcycling thing is coming up almost a decade or more than a decade. So, but these days is a real hot topic for a upcycling. It's not only the plastic, any material upcycling or any material recycling is also okay. But the main focus will be on the plastic because that actually triggered this thought process of decomposing the materials after use. Okay, so otherwise it's not going to be be a sustainable approaches. Okay, so what is that recycling and upcycling, and how it is connected to the green chemistry is green chemistry principle 10, design for degradation. Okay, so any product you are making, at the end of its use should be decomposed. It should not persist with the environment. It should not stay. And it should decompose into a non-toxic products. Okay, so when you say its use means the use is timeline will be varying from different products. Okay, but once you say that I don't need this anymore, this should have this. It should not be existing in the environment and it should be degrading in it. So this is what actually we missed while preparing the using the plastic. People have not thought about its chemical reactivity. Okay, so it's a little inert. That's for good, say one side is a good, but it is inert, the other side is a bad also. Okay, I will tell you in terms of chemistry why those things are so important, the decomposition. Yeah, this is what, see, everywhere you see plenty. One solution we found for a bio waste and other things, but this is also a problem everywhere we have. So what are we doing right now is we are doing a recycling. You may be getting some lot of news articles. Okay, you see this, the plastic is used for making the roads, some other country, some place in our India also, some few places we are using. Okay, or we can use this plastic after use, like a water bottle is there. Okay, and these days every house you see this kind of things. In the schools also they say that the title is very interesting actually, because my kids will make a lot of toys and other things with using plastic bottles. Yeah, waste to wealth. Yeah, something interesting in the school. Every year they will have some competitions, they will conduct and ask them to give some innovative way of reusing, recycling. So what it means is, you see the definition of it. At the end of its use, you are not using it for its original purpose, but something else. But during that process, as a chemist, if you see, there is no change in its chemical structure. Whether it is this bottle or the bottle filled with the water, its chemical structure is same. Only its usage is different. So originally it is designed for this purpose, but now it is used for this purpose. There is no change in the chemical structure, no chemical properties. Still it cannot decompose by itself. It will take 400 years. This also will take 400. Same thing only, right? So that is called recycling. Okay, you are not changing any of its properties. Only its utility you are changing. Usage you are changing. Remember this. Okay, and this is what is now. You can crush the plastic materials and use for a road, paving the roads also. Lot of places people are doing this these days. They crush into a small powder, small particles and pave the roads. It's after all a hydrocarbon. Traditional plastic is nothing but a polyethylene, polypropylene mostly. It's after all a hydrocarbon, polyhydrocarbon, right? So even by cutting that, you are not disturbing the chemical structure. Only chemical structure is as it is, a molecular weight, everything is same. Only the size of the material you are cutting, not size of the molecule. Remember this, not size of the molecule, only size of the material you are cutting. So that is what it is. If you don't understand, this is what is a recycling. Okay. So there is no chemical structure change, and this is already in use, people are using. But it is not solving the purpose of the landfills, the waste accumulation, plastic waste accumulation. After 2-3 months, you see, throw this bottle again. And you take a new bottle and cut into this shape and fill the mud and grow the plants, and you throw this because it looks very ugly or shaped out, right? But again, it is coming back to the same original position. So it's not going to solve the purpose. It's only just making another use, giving another use, but not a solve purpose, right? You agree or not? So this is okay. And this is what the industry does. I will just show you some chart. What happens? Plastic waste. You see the lot these days, people with the bags on the roadside, they collect the plastic materials, right? So what they do is they sell it, a vendor, and he will collect and transport to MRF, recycling center, cleaning, sorting out different bottles, different properties, different chemical structures. They sort it out and then shred it, washing, melting, reorganization, whatever. All this process, you can make a new product or something or other thing, but you are not changing the chemical structure. It is the same thing coming back and it is there. Okay. So this is a good chart for a recycling thing, plastic recycling thing people are using. I will not give. And you just remember this. It takes about 30 days. If somebody collects the plastic waste today to come to the useful meaning in this way, not that what we use at home, that is takes only at 10 minutes to cut the bottle and use it. But this process takes about 30 days to get into the meaningful reuse. Okay. Yeah. Okay. Let's go back. So to the chemistry part of this, so that will be helpful. So whatever we have seen, the recycling, as clearly mentioned, there is no change in the chemical structure. So it is only a limited usage. But the idea of this disturbing the chemical structure came into the scientist's mind, so that whatever the plastic waste or whatever the used plastic is there, that can be converted into some again useful products. Again, you need to look into that bottle as only a chemical molecule. After all, it's a polymeric alkane. Then, but how do we decompose into that? So that is what the origin of upcycling. Okay, so I will give in a minute the upcycling definition, but these are some of the structures of the polymeric materials or plastic materials which we use: polyethylene, polypropylene, polylactic acid, polystyrene, PVC pipes, PVC. So this is a polyvinyl chloride. The material is used is a polyvinyl chloride, which is used very well, like in our home also, like agricultural thing also. And there is another interesting example, particularly polylactic acid, polyethylene. Remember, these two are not that toxic. At the end of the 10 slides, you will come to know why these two are not that toxic. Means they can decompose. Their lifetime is very less, but these things lifetime is very high. Even the PVC is little better, but not the other things. Okay, so these are the chemical structures. If you look at carefully, all of them mostly the hydrocarbon based things. There is a like heteroatom, like ester group is there. There is also a polyester. Okay. Yeah. So what is upcycling? That why I shown you, it makes sense now. The upcycling is also a like reuse only. You have to reuse the material, but you disturb the chemical structure now. Okay, it's not that as it is with the chemical structure, whatever the originality is there, you will be using, but you disturb this chemical structure and make a different chemical entities. Okay, and that is called upcycling. So that's what, you just change it things. So you just take a plastic bottle, and I have shown you that these are the chemical structures. So I know, suppose if you know a chemical reaction which you can break a CC bond or CH bond, make into a small molecules. Earlier in the bio waste, you are degrading a polymeric material into a small molecules and stitching, right? Same principle here also. This is a polymeric structure. Either you can cut into a decent molecular weights or in a small molecules, whatever it is. Once you disturb the chemical structure and make some other chemical entities, a small molecules, a decent oligomeric molecules, what she was asking, like, okay, little larger molecules, but whatever it is, you are disturbing the chemical structure, and that is called upcycling. And this is recently a hot topic, because lot of new things you can actually synthesize from this plastic waste. Okay, so the recycling is using as it is, upcycling is doing a little bit of chemical change to the molecular framework. Okay, you can do any type of chemical reaction which disturbs its properties, the original properties. Okay. Yeah, so just I will give you a little bit history. There is nothing much. So the plastic, whenever we talk about the upcycling or a problem of plastic, okay, remember there are only two plastic materials, or whether we call it traditionally plastic, polyethylene, polypropylene. Even now they are in use and they are still dominating the plastic industry. Okay, so why they are really dominating is they have a very flexible properties, very flexible and very diverse applications. They can sustain lot of photochemical conditions, thermal conditions, even chemical conditions. They have the tendency, and by changing slightly the chemical structure with alkane only, okay, you can fine tune their properties. That's what I told you just before. You cannot stop avoiding using the plastic. Better you find a way to reuse it or upcycle it, because it is spread such that everywhere it is, and it is a good only. For good applications it is there. Only thing, at the end of the day, decomposition is a problem for us. That's the only problem. Other than that, there is no problem at all. Okay, and you may be naming 100 new things, plastic materials, okay, which comes for replacing the polyethylene, polypropylene. None of them can replace. Most of the properties you cannot replace, because the whatever we are getting the new materials. If you see these days, if you go to the shop, you see that plastic bag I told you, it's like a biopolymer, biodecomposable. Yeah, which means it decomposes faster, which means it has a limitation. It cannot be used in some places where you have high temperatures, light, sunlight, exposure, chemical exposure, because it just decomposes very quickly. And that is where it cannot replace the plastic, the traditional plastic. You understand? So one way it is good, it will decompose, but other way it is not good because it is decomposes very quickly. It cannot sustain for many conditions. So that is also not good. So that's what I said, we cannot replace that polyethylene, polypropylene things. So a little bit history, as I told you, about 1933, we are just approaching 100 like century of plastic invention. Okay, and it came into use in 1950s into the market. This is what, okay, these are the people who used it. And what is the polyethylene structure? What is the ethylene first? C2. Very good. What is the chemical formula? This is a structure. This is a chemical formula. Very good, right? So when you say polyethylene, many molecules of ethylene combined together, which means it's a self, right? So you see that this carbon-carbon double bond will react. So just to make you understand, carbon-carbon single bond is there. I will not say that it's a radical thing or anything. There are radical mechanisms, ionic mechanisms to polymerize many things. Just for your understanding, okay? You can just make a two reactive centers. So just cleave that pi bond and put one electron here, one electron here. Another one I will write. Okay? So they can make bond, right? But this is not the only mechanism. Okay? The ionic mechanism, just for your understanding how they polymerize. So now, at the end of the day, this you have, right? Pi bond. Now what is happening is, right, that pi bond is lost. All you have is carbon-carbon single bond, carbon-hydrogen bond in a polyethylene, polypropylene. When it is a polypropylene, it's the same thing. One extra methyl will be there in place of hydrogen. It's a propylene. Propene, nothing but propene only, right? So it's a 3 carbon unit, it's a propene. So now, instead of this 2 carbons, so everywhere you will have a 1 methyl. This is a polypropylene. If it is a H, polyethylene. So I will just keep it simple R. So what happens is, so when R is equal to H, polyethylene, PE stands for, and when R is equal to methyl, polypropylene, when R is equal to PH, polystyrene. Styrene is nothing but, you know, pH. Methyl replaced with a pH, styrene. Okay, and vinyl chloride, that is easy, remember, you can remember easily, a chlorine. So now if it is R is equal to Cl, polyvinyl chloride. You understand? Everything is nicely summarized, can be summarized with a simple formula. H, methyl, phenyl, chlorine. These are the things, okay? So, but all of them except this, only the polyvinyl chloride has a CCl bond which is slightly reactive. Hetero bond. When I say hetero, anything other than a carbon, hydrogen is a hetero. We can label in organic chemistry. And everything is a hetero, which means not the same family. Okay. So this is what the structure, and that's what I have shown you earlier. And these are the some of the materials which we use for this one. And as I told you, there are different types of polyethylene materials we will be can be making. Only a few of them I have shown you. For depending on the usage, what is the purpose you are going to use, okay? And accordingly you can control this structure, chemical structure slightly, but you will have only the carbon-carbon bond and carbon-hydrogen bonds. Only the chain length and the other things will be changing in the polymer. Accordingly, you can fine-tune its properties. Yeah, let's come back to this. So this is the CC bond energy about 83 kilocalories per mole. This is a CH bond energy which you learn about 90 kilocalories per mole. These are the like two of the strongest bonds you can see in chemistry. Okay, as covalent bonds. If you take CO bond, CN bond, CX bonds, any chlorine bond, the energies will be slightly lower. And it's not when the energy is lower, not always energy is lower, but the tendency of its reacting it with something else is much higher. It's after all a simple chemistry, nothing more than that. Okay. A carbon-carbon bond, both of them are equal, is a strong covalent bond. There is no polarization of electrons at all. Even almost the CH bond also, if you see the electronegativity of a CH, carbon and hydrogen, they are almost close. So you don't see any polarization, electronic polarization. They are real pure covalent bonds. But if you go back to the CX, X can be anything. Okay, halogens. Usually X we use for halogens. So there is a polarization. These are all highly electronegative atoms, relatively higher electronegative than the carbon, which means the electron flow will be here. Slight movement will be there depending on the difference that you learn in your atomic properties. Okay, so which means that there is a polarization. There is a induced. So which means the carbon is feeling like electron deficient. No atom wants to be electron deficient and no atom wants to be electron rich also. Always remember, both of them are very uncomfortable situations for elements. They want to lose out that situations. So when this is there, see that when somebody is pulling electrons there, we need some assistance. Similarly, when it is trying to get, by its virtue of its nature, it's getting a more electron character, electron rich character. It wants to lose. Which means now you see that the losing and gaining, the tendency is built in the molecule. That is what is called a reactivity, right? It doesn't want to stay in that form, but here it is slightly different. So that's what even there also in the fuels also I said, they are a little bit reactive. So this is one of the reason why our polyethylene, polypropylenes doesn't decompose, okay, on its own, naturally. It takes hell lot of time to gain that activation energy because it needs some assistance, catalyst, promoter, energy, either from sunlight, thermal, so whatever it is. But it will take a lot of time. So this is one of the very reason they doesn't decompose. But at the same time, that will give them the wide applications in the usage because you can use them at high temperature packing materials. Okay, when you have something to protect some material, you want to protect from the light, you can use them because they are not sensitive to the light also. Temperature, there is a limitation of temperature. They are not sensitive to the chemicals also, very standard chemicals, right or wrong? So until so which means they have more applications, particularly the packing and protection based things. So these will have a lesser applications. Okay, means they have a little bit more sensitive things. So that is the reason the polyethylene, polypropylene cannot be decomposed. But how do we do that now? I said we cannot decompose from nature. Nature cannot decompose them as it is. It will take 400 years. But we can do in the laboratory. We can take them, we can do the chemical reactions, a focused chemical reactions, and we can degrade them. Right? We do we break a lot of carbon-carbon bonds, carbon-hydrogen bonds while making materials in synthetic chemistry. Right? So we can do that, but it's a focused. You should know what exactly you want to do. So reagent, catalyst, everything. So you can do a simple chemical reactions, and what you can do is convert them into some of these reactive bonds. Okay, so you have to induce some reactivity in them. Then you can easily decompose. So for that, people will be using a lot of chemical approach reactions, and that is a chemical upcycling. So people use this reaction based chemistry approach to upcycle them. So convert into a small molecules, degrade them. So it will not go back to the ethylene, it will not go back to the propylene, but something else. Some other chemicals depending on the conditions what you are using. So you can have control that, what you want, what type of material you want to prepare it. Okay, but again, it's not right now. It's not really efficient because there is a limitation. You get the controlled reactivity is slightly less. So you see that multiple reactions happens, multiple degradations happens. You see, but there are methods people are using chemical reactions to decompose the plastic, particularly the hydrocarbon based plastics, polyethylene, polypropylene, polystyrene. These are all pure hydrocarbons. Remaining all you have some reactive bonds. It is easy. When you have a CCl bond, you can treat with the base. So it's sensitive to the base. You can cleave that CHOR. You can do the elimination reaction, make the olefin, carbon-carbon double bond. Okay, so likewise, people actually decompose this, and that is what is the plastic or polyethylene, polypropylene upcycling. So I will show you a few chemical reactions. Try to understand. Okay, don't look at the catalyst structure and just get scared. It's a simple. You yourself can design after 4 years or 3 years when you learn a little bit more about the chemistry. But what are the chemical structures? What is the principle involved? Okay, whatever catalyst people are designing to do this chemical upcycling. Okay, that we will be learning. Yeah, so that's what I said. So don't worry about by looking at these complexes. These are called catalysts. Okay, so because there are some metals which actually easily bind to the CH bond or CC bond. In the periodic table, if you see particularly the transition metals, okay, the D block elements, if you see, there are metals and the complexes what you make from them will have a tendency to easily insert into the CH bonds and CC bonds. So people are actually exploiting that reactivity, their reactivity for activating the polyethylene, polypropylene. It's a elemental property, but now we can use them for doing this purpose. Okay, so you should know that properties also, and you should know the organic molecule properties also. So you can combine them. That's why don't worry about all these things. So these are iridium. These are like what you can say, lanthanum. This is also iridium. What else? Which means why? So there are plenty of metals in the periodic table, but we choose only few because they are easy to react with the CH bonds and CC bonds. And one such one is iridium. Iridium based complexes, they nicely interact with activate the CH bond, sp3 CH bonds, particularly CH3H bonds. Okay, there are other than that many other metals. That's why in this chemical upcycling of polyethylene, polypropylene, mostly right now the iridium catalysts are dominating. Only thing, they change these ligands, the coordinating units of the your metal ion. Okay, just to increase its reactivity or protects its reactivity. That different people does with using different molecular things. Okay, that's don't worry. But the purpose is to activate the CH bonds. Now you see that there is a iridium catalyst used. There is a like plastic. These are all research papers. Okay, it's not industry papers. These are research papers which were done in the laboratory. So that catalyst does this activation. You see that it randomly creates a carbon-carbon double bond by some mechanism. Okay, so don't worry about the mechanism, but it has the tendency. That's what I said. So you can activate randomly anywhere. It has the tendency, and you create the double bonds. Here also you can see the double bonds. Now, once you have created a unsaturation in any molecule, organic molecule, that is the source of everything. You can do n number of functionalizations using a carbon-carbon double bond. You can do oxidations, you can do reductions, you can add halogens, amines, water, oxygen, anything you can do. So that is a tricky part, creating the carbon-carbon double bond, because you have to remove the 2 hydrogens. This is a polyethylene, right? So let me just put like this only, right? So you can create this kind of double bond. Suppose you take a vinyl chloride. Suppose this is there. This bond, chlorine. This is easy to remove because it has a tendency to take its electrons. So, and then that will actually makes this delta positive. Okay. And once this has a tendency to go as with the electron density delta positive, and it wants to be quenched, so it will be losing. So this elimination reaction, creation of double bond from this kind of systems is much easier. But removing two hydrogens and creating olefin is very difficult because none of them has a tendency to go away as a H minus. H hydrogen cannot hold the 2 electrons. It can lose 1 electron and becomes H plus. But you don't see the H minus. H minus can be found, but it is highly reactive. It wants to lose its H minus character because the hydrogen cannot hold the 2 electrons. So it will react with any proton source or anything and it will be quenched by itself. Okay. So that's why, so these catalytic systems people use to convert into this. So once you have that, plenty of reactions you can do. You can use a vaginolysis to cleave the carbon-carbon double bond and make a small molecules, a degradation. Or you can add a heteroatoms, anything. So that's how people are actually functionalizing. So first step is to activate or make it towards the activation, slight activation. This is what, so people, a lot of research is going on and one of them is iridium based catalysis. Okay, you understand? There are other metals also people use, but this is actually leading. So you can see that there is another type of approach, but ultimately, finally you see that you are making only the double bonds because you have an alkane, you need to make it first slightly active. For that, what people are doing is a light and a bromine gas. You learn this alkanes halogenation reactions under light using chlorine, bromine, right? Same simple chemical reaction what you learn is used here because after all it is a polymeric alkane. Why you think that it behaves so differently? It is also an alkane, like as good as your ethane, propane only, right? So people, you can use a light and bromine and do this halogenation. Once you have, it's easy to, just now I said, it's easy to make this. Just add a base, it will undergo the elimination and you get the double bond. So the advantage of here is you don't have to go for this strange complex catalytic systems. Using a natural light and a bromine gas, you can do the same, generate the similar kind of molecules. Again, so different people think in a different way to do the same purpose, to give the same solution. Okay, and similarly, there are many, like palladium also. So don't worry about that. Okay, so but I just want to show you what are the varieties of approaches people are using just to activate your polyethylene, polypropylene. After that, now you are decomposing. So your plastic is no more waste and it is not accumulating. You are just taking and degrading into a small molecules. Okay, many molecules we can make, different molecules. Okay. Okay, even you see that from plastic to polyethylene to the fuels. Fuels are nothing but simple hydrocarbons, right? Just now we have written here, right? So if you can selectively cleave the polymeric, suppose C1000 is there, your polyethylene structure is there. You cleave it selectively into a C10 to C15 alkanes. That mixture is nothing but your petrol. So plastic can be converted into liquid fuels. Of course, it is a process. It involves a lot of steps. So, but you have to cleave. We cannot directly use the plastic as a fuel. Why? It is also an alkane and we also need alkane. Why can't we use a plastic? Because it's a polymeric structure, bigger structure. The burning is very difficult. All you need is small molecule for a fuel to burn easily, right? Because if you use a polymeric structure, it doesn't burn or get cracked into efficiently and it is not an efficient fuel. So you see that all the smoke comes. If something doesn't burn properly, what it means is it's not actually taking oxygen properly. The reaction is not happening. So you see the smoke only, right? So the energy is not coming out efficiently. So you cannot, in principle, you can crush the plastic, but as I told you, when you crush, you are not disturbing the chemical structure. Same polymeric structure is there. So as long as it's a larger structure, you cannot burn that easily. So you need to crack into the small molecules. Okay. So that's why that polyethylene, there is a procedures, people are, the chemical procedures they are making. Yeah, somebody is raising hand. That's what. So pyrolysis is also one way of cracking, small, this one. But what happens is there you should not burn them because there itself is a high temperature. If as soon as you make your fuels, they themselves can burn. You understand? So that is also one way people do that. High temperature procedures also there. I will show you. So that is another method. This is also a method. Okay. Yeah, there are methods, okay, so don't worry about it. Yeah, even this we have seen, right? Yeah, answer to your question. So if you use a high temperature thing in presence of oxygen, you can make this kind of oxygen based molecular frameworks. Okay, so it's possible. People are doing again. It's not that only limited to the double bonds, but now you need like a strong conditions, very strong conditions, a very strong acid and a peroxide, 200 degrees or 180 degrees, very strong conditions. If you use higher temperature, then what happens is they themselves will burn out. Then you are not getting anything out of it. So there should be a much control procedures to isolate the products. Otherwise, they'll at the end of the day you make only a ash. Nothing will be there, right? So you can make different products also. Not only the like hydrogenation, like dehydrogenated products. You can make even oxygenated products also. Yeah, another one is polystyrene. This is also very important. So polystyrene comes from this pH. So you will have an extra pH here. So there are a lot of these are the different methods I have summarized. So this is a polystyrene structure, and people make benzene based molecules, benzoic acid, benzaldehyde, or acetophenone sometimes, because it is the monomeric unit is benzene and with the 2 carbons, right? So people selectively do the cleavage at every 2 carbons or 3 carbons, and you see that the benzene based molecular things can be generated. So you are not going back to the styrene, you are generating a benzoic acid, benzene derivatives. So that's what is the upcycling. So you are not really regenerating the original or you can say the monomeric unit here. Yeah, you can see that various methods are there. Here you get a benzoic acid, some places you get only benzene, some places you get a benzaldehyde, various different depending on the condition what you give, the polystyrene will be converted into different chemical entities. Yeah, you can even, there is a method, say hydropyrolysis at 800 degrees. If you do that, you can get some amount of styrene or ethyl benzene also, which means literally you are depolymerizing into a monomeric unit, 100% monomeric unit, but it's not very efficient. Overall, from here to here, they get about 92% yield, this process. But this process is slightly less yielding, so it needs a lot of upgradation, okay? But the evidence is there. It is possible. The evidence means it is possible. Okay, so this is the last slide, but lecture is not over yet. So there are various polymeric materials these days we use. I have shown you polycarbonate materials which comes from the epoxy and carbon dioxide, polycarbonates. This is also a polycarbonate. It repeats. A carbonate, sorry, it's a carbonate. Okay, it repeats, polycarbonate. So these are also like what you say, we are using a decomposable plastic materials. Most of them will have a polycarbonate materials these days. You go back and read that the chemical composition, most of them will have a polycarbonate materials. Why they are so easily made? Because their resources are coming from a bio waste. So people are more into that. That's good. But the problem here is how easy it is to decompose. You just take a polycarbonate, add a K2CO3, slight heating, the polymeric material will decompose. If you take a plastic, our traditional polyethylene, you add K2CO3, nothing will happen. Even strong sodium hydroxide you add, nothing will happen. There is a difference in their response. So which means this is good to use and easy to decompose. The easy to decompose is actually bringing some limitation on it, because as I told you again earlier also, you cannot use these materials everywhere. Like your polyethylene, polypropylene, there is a limitation, because just imagine you are exposing these materials to a slightly basic conditions somewhere in the storage. It will decompose. You cannot use them for packing under the basic storing your material, your products under the like basic conditions, or it will be sensitive to even the light also. It will undergo the decomposition and release of the carbon dioxide easily. So the decomposition, easy decomposition is also becoming a problem. So we cannot use them everywhere. They are easy to disturb. So we can use them, you can decompose, but again the limitations are there on their use. That's why we cannot replace a polyethylene. Okay, as a chemist, that much only I can tell you. You have to find out as a chemist, we have to find out methods to decompose or reuse them, polyethylene, polypropylene, but we cannot replace, because all these things are a temporary alternatives, a limited usage, but they will not 100% replace your traditional polyethylene. The reason is simple, because they are reactive. They have reactive bonds. That's what I am just showing this slide. Easy. K2CO3. We have not seen. We have seen all the very complex catalytic systems, high temperatures when you are decomposing the polyethylene. Here you see that very simple condition decomposes a polymeric material. Right? So there is a limitation for it. Yeah, that's what the answer. So we cannot remove. So we need to find out the alternative methods. Okay. So if somebody asks that why the government is not stopping the production of plastic, this can be one answer. There may be other answers, the solutions, the political things. That's none of my thing. But the chemically, academically, I can tell this is what it is. Okay. So there is a limitation of properties, limitation of usage of biodecomposable or decomposable polymers, plastics. Okay. So we have to go with it. Thank you. I think that's all. I hope you learned something. A very general. Okay, I don't want to teach a very standard chemistry or anything. It's a very general, but everybody should know. Okay, these topics, the green chemistry based things.
Sir, we are truly thankful to you for continuing this enlightening session on applications of green chemistry today. Your discussion on conversion of biomass to fuels were particularly fascinating. We deeply understood on classifications of waste into three key components: the hemicellulose, cellulose and lignin, and their conversion to biofuels. Through this, we understood on how nature's own resources and waste can be harnessed for greener future. We also understood on how the harmful plastic can be recycled and why it is difficult in nature to decompose polyethylene and polypropylene. And we also understood the chemical application using upcycling. Therefore, through these applications, we learned how important green chemistry is in today's world. Once again, thank you, sir.